All right, good morning. So, as usual, before we dive into the lectures, let's see what you should really pay attention to. For your programming test 1, still, if you want to go over your submission or the solution, feel free to come by. My office hour today is a little bit different, but it will be extended. It will be from 1:30 p.m. to 3:30 p.m. for today. Drop by anytime if you wish. Otherwise, you can feel free to send an email to Andy, but he will happen to be also in the prison lab. Sorry, not the prison lab. You can check the room. It's actually on the smaller lab in the Lausanne building. So that will be, I believe, from 2:30 to 3:30 today. You can make use of the resources. And for your lab number 3, it will be due tomorrow, 12 noon. Right? Just make sure you submit in time. And for programming test number 2, I just released the guide on the lecture site. Right? And for the practice test, I'll try to make it available to you by the end of tomorrow. And I'll make the solution to you also on Monday. So give it a try over the weekend. All right, let me show you very quickly about the programming test 2. There could be some clarification that's worth making. So if you go to the lecture site, you will see under, over here, you can, oh, sorry, maybe I need to refresh. There we go. So programming test 2. Okay, it's going to be next Thursday. So next Tuesday still come. It's going to be the last class. I can talk briefly about the exam. So next Tuesday. So we still have lecture next Tuesday. But Thursday, we're going to have your final test for the semester. Policy-wise, it's really the same as last time, but I can read it through just in case you forgot the policy. And so this bullet point here, excuse me, this bullet point here is consistent with what I said last time. So there will be 2 parts for your programming test 2. Part number 1 will be about the formal specification of a context, like a part 1 for your lab 3. That one will be roughly, approximately 60%. Could be 60, could be 55, but around that range. And the remaining part will be the manual proof that you're supposed to do, okay, for your lab number 3. So if you're really struggling with the prover, you still have time to learn it and get help. But in the actual test, if you really suffer from getting that to work, you can still get, hopefully the majority of the marks for the test. So the intention is, hopefully you can get passing. All right, so the penalty about having some errors in the project is the same as last time. That one I haven't changed. And I will still make this available to you during the test because you will need rodent syntax to get things to work in rodent. So this PDF will still be made available to you. And the format will be identical to your lab number 3, right, as I said last time. So this is just to make it formal on the paper, okay? And the coverage, you just need to study for lab number 3. But since the actual formulation in the part 1 is going to be about defining mathematical objects in rodent, so it wouldn't hurt if you want to review the lecture, the math review lecture, or maybe look at the lab number 2 solution, or practice test 1. They might help. Okay, it's up to you. But I think it's mainly lab 3 that you have to study for. All right, over here, practice question. Yeah, I'll give it to you. I'm still working on that. I'll release it by the end of Friday tomorrow. And solution will be before your Tuesday's class or Monday. All right, and this is just how you can simulate. Oh, one thing to note, right? There's something that will also be said in the practice test. For this programming test, let me show to you where you can find that description. Oh, here. So you will not be expected to set any proof tactics in the actual test. We're going to save you some time. So what you will be given to start with will be some instruction PDF plus a starter project. So all you have to do is to import that starter project into rodent, and everything will be set up for you, so you can start right away. Okay? So I will try to make some similar starter project available to you in the practice test. You can definitely practice. So everything should not be surprising in the actual test. Okay, so guys, any question about the programming test 2? Anything that's kind of not clear to you, what to expect? Okay. Alrighty, and let's see. And I think that's about it. All right, so if you have no further questions, then let's now do a quick recap about divergence that we cover on Tuesday, and then we'll move on to Deadlock freedom. Okay, last time we actually started the idea about divergence. If you remember, this was the trace that we actually work on to say if you got an indefinite interleaving of the new events in the concrete model, it will simply correspond to skip, 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 like a busy waiting in the abstract model. So that's definitely something you would like to avoid. But simply coming up with the trace like this is actually quite time-consuming. It's not that easy. So the way to formulate the check on divergence, which means you got infinite interleaving of the new events. You can never have all events like an MLR or MLN ever happen. To really avoid it, you want to have some systematic check. So that's why we introduced the idea about system variant. So we also did some comparison about invariants, right? So now you should really know the difference between these two, right? We'll talk about them in detail. And we also try to trace very much in detail over here to see how the values for the variance should really change along the event occurrences. You want to make sure you review them. That will give you much insight. And then from there, we generalize two proof obligation. One will be called net. The other one called var. This one here tells you that the variance should be larger than or equal to 0. Should be a natural number. Should always on or above the 0 line. And the second one tells you if you ever want to have an occurrence of the events, of the new event, it should really strictly decrease the value. Okay? That's something you want to keep in mind. All right, so these are the two you want to make sure you understand. Of course, in the data sheet that you're allowed to bring to the exam, feel free to put anything you like. But if you want to think about what you want to put. Right, so this is where we were, right, about the proof, the inference rule. Oh, one more thing I would like to show you before we carry on with the discussion about inference rule. If you look at the lectures page, I have added some extra study materials for you, okay? So if you look at on the side over here, I'll make it a little bigger. So if you look at the notes section over, oh, by the way, the slides has been updated. So now the slides are pretty much complete about the initial model and the two refinements of the bridge controller. That's what you have to study for the exam. And we'll hopefully can really go over the majority of them today and also next Tuesday. There might be some very minor amount that will be left, in which case I'm just going to use up the remaining time for your makeup lecture. And wouldn't be too much, but I'll release that as soon as I can if we need it. But the slides are pretty much complete, and all the inference rules that you're supposed to know for the exam are also here. Okay, so now not only just the two that you actually study for your written test number 2, but there's some extra 2, which we'll talk about today as well. Okay, and you will see that some justification video about the inference rule that we spoke about last time. And also, these are some notes. These are pretty much the proof that you will see on the slides, but in a more readable form because it's actually larger font size. You can feel free to print them out or load on your tablets and you can study the proof together. Okay. All right, so that's about the materials you want to be aware of, so you wouldn't miss them. Okay, so we started with the third set of inference rule last time, right? So this is what we talked about last time. Let's take a quick look, and then we move on to the other two. Okay. So this one tells you if you have the disjunction to the right of the turnstile, which is over here, that means you want to prove the goal that's either P or Q, right? So we talk about ORR1, for example. If you say OR, you want to compare, right? Which we also did last time. If you, oh, actually exactly here, forgot. If you got ORR1 over here, one way to really transform this sequence over here would be, you can say, if I want to prove P or Q, I can choose to prove only P, or I can choose to prove only Q, right? And now there's another possibility for you. You may want to say, okay, I don't really want P over here. I don't want the P to be a goal to prove. I can move it as one of the hypotheses, but I need to negate it. To really see why, you have to understand this is the justification, which we mentioned. So there's a link on the lecture site, which will walk you through about some nice proof, which is pretty brief, but that will be very sensible for you to follow. All right, so that's the inference rule. So guys, any question about this rule? Anything that's not clear to you? And if I were you, there will be one simple sentence I want to put on the data sheets, okay? Just in case you forget. Because there will be so many inference rules that you may have to apply in the exam. What if you forgot about how to read the inference rule in the exam? In that case, that's pretty disastrous, right? So I would say put a single sentence there to say, if you have, for example, let's say you got some sequence number 1 and you got sequence number 2, right? Let's say. And in this case, what does it really mean? That means to prove S1, it is sufficient to prove S2. That order is really important, just in case you forgot, right? Even though you're so confident right now, but you might be nervous on the actual exam. So I would suggest put this one, which wouldn't take much space. All right, so let's now take a look at another 2, okay? And for this one here, okay, let's read it together. Here we say, if the conjunction happens to the left of the turnstile. So this means we got some hypothesis, which itself is a conjunction. In that case, easy. We can separate them into 2 different hypotheses. That's why it's pretty easy. I may even maybe set informally. Whenever you see comma over here in the hypothesis, they simply mean conjunction. Okay, this one also can be useful. Sometimes when you actually first formulate the proof obligation, you may have some conjunction over here. But you might find that one of them actually is actually more useful than the other. In that case, you can split them into 2. Okay? And the third one here is also very important. Okay? This one here is to say, if you have, let's read it first. If you got conjunction that occur in the right of the turnstile, which is over here, right? To the right. That means you have a conjunction of conjunction to be proved is a goal. In that case, you can split it into 2 sequences to prove. I can try to prove P over here, which is the left. I can also try to prove Q over here to the right. But I need to make sure both of them are provable. Right? Do you find any rule that you learned before looks quite similar to this? I.e., you can split a single sequence into 2. Wallet. Absolutely. Thank you. So guys, if I were you, I will also check to see ORL. Okay, compare. So these 2 are very similar, but you got to be careful. Let me just maybe verbally summarize very quickly. In and R rule, if you are given a conjunctive goal, you can split the original sequence to prove into 2. And in the case of ORL, if you have a disjunctive hypothesis to prove, in that case, you can also split the original sequence into 2 to prove, right? So I'll just give you some quick summary here. So given a disjunctive hypothesis, and you can also split. And check the detail, please, in the original rule. All right, so these are the 3 we need to learn. And some of them will be useful when we actually try to prove some proof obligation that's going to happen very soon. Okay? All right, guys, any question about these 3 rules? Good? All right. Okay, having said this, let's now talk about this subject here, about relative deadlock freedom. So one thing to note, when we actually did for M0, the initial model, what we prove is about just deadlock freedom. Okay? However, when we get to some refinement model, what we have to prove, since we got abstract guard and concrete guard, we have to add the word relative deadlock freedom. Relative in the sense that you have to somehow relate the guards in the abstract model and the concrete model together by using some logical relation. That's something we'll see, but before that, let me go over some bullet points and then we'll get to the illustration. Okay, so this is what we discussed last time about the variance. And there is one exercise that's on the slides. I'll show that to you over here. Okay, the variance that we talked about last time was 2a plus b. Exercise for you, try just a plus b. Are we still going to be able to discharge the proof obligation. And also try to trace both things. Okay, that's an exercise for you. So in the exam, I may not ask you to really come up with a variant from scratch. That might be a little bit too difficult, but we'll see. Let's say if I didn't do that, in that case, I might just give you one candidate variant. We'll give you several and say, okay, now choose the one that's correct and justify it, right? So in that case, if you don't think this is appropriate, in that case, you want to justify to say why. Because it might fail certain proof obligation proof, okay? Okay, so let's talk about deadlock freedom. What we did earlier in M0 is we proved that M0 is deadlock free, okay? And then here in the refinements, we did something kind of similar called guard strengthening. But that one there, I don't want you to really get confused with the deadlock freedom. But this one, I want to mention that over here. I'm going to do some comparison, to sketch very soon. But let me talk about relative deadlock freedom first. But for guard strengthening, that's something you want to also compare side by side a little bit later. Okay, this will be the proof obligation the proof obligation rule for deadlock freedom, relative deadlock freedom. Let's see how we can understand this, okay? Let me, first of all, show you where the tricky thing, the confusing thing is. If you recall, we got guard strengthening. Let me put it down first. Guard strengthening. Right, that's what we did earlier. And then I'm just going to give you the relevant details. So we got something over here, and then we say the concrete guard should be stronger than the abstract guard. Okay, so that's what you want to also recall the details. Okay, so this guard strengthening. Okay, so that one there basically say if the concrete events is enabled, then the abstract counterpart is enabled, right? Okay, so let's say this is the abstract and this is the concrete, right? Concrete and also abstract. All right, so that's a very quick recall. All right, and now, if you look at the proof obligation rule that we're talking about, oh, by the way, the name here is also called DLF. So whenever you're getting DLF, proof obligation, you want to know whether you're talking about DLF in the case of refinements. In that case, this will be relative deadlock freedom. Deadlock freedom. Okay, kind of relative is kind of implicit in the case of refinement. And notice the thing here. Here we got H implies G. But here we got G implies H. How can that be true? Well, how can that be the case? Since we're not being consistent. So that's why I said you don't really want to confuse the guard strengthening idea with deadlock. You want to treat them separately. Okay, that's number one. Number two, you want to see the actual rule over here. Before that, what should you use as the other hypothesis? So over here, you can see we got axioms. So for this part here, so we got axioms. We got abstract invariants. Also, we got concrete invariants, right? So these are pretty much standard. And guys, what is this? Can you read it? Yes, exactly. This one here is a condition. You can see we're trying to do disjunction of all the abstract guard. Okay. So what you really want to what you really want to convince yourself when you study for this. Okay. So this one here, okay, it is disjunction of all. How about this? Of guards of all abstract events. Okay, abstract. That's a disjunction. And what does that condition really mean? That means under what circumstances is the abstract model not going to deadlock? Okay? Circumstance for the abstract model not to deadlock. Right? It's really important to really see some intuitive meaning here first. Okay? Right? Symmetrically, let's look at this one here. Right? This one here. Let's use the red one here. I'm going to have a very similar description, and then we're going to visualize it together. Okay? This one here basically is a disjunction of guards of all the concrete events. And I'm running out of space, so you can write this for yourself. We said before this guy over here is the circumstance for the abstract model not to deadlock. So what about this one here? This will be the circumstance for the concrete model not to deadlock. Okay? And by having the turnstile over here, right? And we know that turnstile is really about implication. Okay? So we're basically saying if this is the set of states where the abstract model would not deadlock, and having the implication over here, we say that the circumstance for the concrete model not to deadlock should be like a superset. That's what we are saying. But how do we interpret this relation here? Okay, I'm going to write down some principle for you to understand a little bit more. Okay. So guys, what you have to, again, when you study for that, number one, look at the disjunction over here. And there's an implication over here. The way to visualize it is to say the set of states where the abstract model would not deadlock should be a subset of the set of states where the concrete model would not deadlock. Okay? And now what we want to talk about is this, some principle, which I'm going to write down here. Okay, so let me make some space over here. And there are two principles over here. And since we are now talking about a bridge controller, which is a reactive system, so deadlock is a bad behavior because you don't really want your system to simply stop reacting to the outside world, right? So number one, deadlock is bad. Okay, number one, just agree. Okay, number two, refinements should not introduce a bad scenario. So what do I mean by that? If there's a scenario that we already know is going to deadlock in the abstract world, it's okay to also deadlock in the concrete. But if there's one scenario where it will deadlock in the concrete, but it wouldn't deadlock in the abstract, in that way we are introducing something bad. Okay, I'll write it down. Okay. That means unacceptable if there is a state where the concrete model deadlock, but the abstract model doesn't. Okay, so I would say this principle over here is extremely crucial for you to understand the formula. Okay? Okay, so overall, we just don't want to introduce any bad behavior, which is deadlock. Let's now consider two scenarios. So this will be the case where the proof obligation is provable. This will be the scenario where the proof obligation is not provable. Okay, let's look at the provable case. In this case, the set of scenario or the set of states where the abstract model wouldn't deadlock, they are covered by the concrete world. Okay? So let's say this, thinking this way. You want to look at two states. Any state that's over here. This will be a state where the abstract and the concrete models will not deadlock. Would you agree? Because this state here is a member of this one here, is also a member of this one here, right? So that's okay. What about a state over here? This one here, what does it really mean? This one is important. Wallet, how would you interpret this? Okay, how about this? Let me make it more focused for you. If we are, well, apparently this is what we can visualize about between the abstract and the concrete. If we have such a state, does it mean we are introducing some bad behavior into the concrete model? Yes or no? That'd be tricky, right? Let me rephrase my question again. Well, let me repeat my question. Let's say, again, this is all the scenarios where the abstract model would not deadlock. This is all the scenario where the concrete model would not deadlock. And now, having these states that exist, does it represent the concrete model actually introduced a deadlock scenario that did not exist in the abstract model? Yes, go ahead.
For new events that were in the abstract?
No, here can be, we talk about states, just any state. Let's not confuse it. Let's not get more distracted by the events. What do you mean? You mean does produce a scenario that's bad?
Yeah, because the abstract model is deadlocking, and the concrete model is, right?
Nope. No. The opposite. Okay? Okay, guys, so that's why I'm trying to put all the possible ways you can think about it, but you gotta, let me explain. Okay? Think about this guy here. If this state over here, number one, would you agree, is outside this circle? What does that mean? That means this is a state where the abstract world would deadlock. Agree? Okay, let me write it down. So this is a state. So this is a state where the abstract model deadlock because it's outside the circle. At the same time, number two, is also a state where the concrete model would not deadlock because it is within this circle. Now, are we introducing a scenario that's bad, or we are somehow improving the abstract world? We are improving, right? Because it is something that would deadlock in the abstract model. But now, we can improve it so that in the concrete world, it wouldn't deadlock anymore. So it's good. We're not introducing anything that's bad. Okay? Right? Again, I'm following this principle over here. It will be unacceptable if you introduce something that's bad. But if you're introducing something that's new, like an improvement, that's okay. It's actually good. Okay? Okay, so the conclusion from 1 and 2 is nothing bad has been introduced. And that's exactly what this turnstile is trying to prove. And we can visualize it here. Yes?
State where abstract and the concrete model will deadlock. I think you missed a node.
Which one? Sorry.
At the bottom.
Well not. Yes, yes. Thank you. Thank you. Appreciate it. Thank you. Absolutely. You mean the green one, right? Yeah. Thank you. Absolutely. Maybe I said without deadlock, but somehow wrote differently. Thank you. Yes, absolutely. All right, guys, think about that one there, and let's do another reinforcement. And this will be the visualization where the green one which is over here, is actually not a subset of the red one. So in general, they might just have some intersection. But the green one is not really a subset of the red one. So that's when it's unprovable. Let's now try to understand why this should be not acceptable for us. Okay? All you got to look at will be basically this state over here. How about one state that's over here? Anybody would like to try why this state can actually inform us this particular scenario is unacceptable for a refinement? I'll let you try it now. Exactly. That's good. Okay, let's now try to see that. If that's what you're thinking, you are definitely on the right track. Number one, this is a state where the abstract model will not deadlock because it's within the disjunction of all the abstract guard. On the other hand, you can see this state here is outside the disjunction of the concrete guards. In that case, it's going to deadlock in a concrete model, right? Okay, so we put number 2 here. But that one there is actually a state where the concrete model will deadlock. In that case, we are really introducing a bad behavior in the concrete model that didn't exist in the abstract model. Okay. Guys, are we good? Okay. If you get an intuition or the big picture, that's really good, but you really, really want to look at the proof obligation when you study for that. And of course, most likely you will put this rule on the data sheets anyway. But I may not just ask you just directly to generate proof obligation. I might ask you something that's more insightful. How can you get prepared for that? Understand everything I've said. Okay. All right. Any question you would like to have before I move on? Sarah. Yes, yes.
Yeah, so we have like M0, M1, but let's say we have another one like M2 and M3.
Yes, very good. So you can think about proving this is more like a relative. So here, let's say, for now, we actually got M0, also we got M1, and later on we're going to see M2, hopefully today, right? When you talk about whether or not M1 is a valid refinement, in that way, you have to put the relatives. You have to prove the relative deadlock freedom of M1 with respect to M0. So in this case, the abstract guard will be the guards in M0. The concrete guard will be the guards in M1. On the other hand, once we get to the second refinement, now it's relative. So now M1 will be the abstract model, M2 will be the concrete model. In that case, you want to prove this again. In that way, the disjunction of the abstract guard will come from M1. The disjunction of the concrete guard will come from M2. Right? It depends on which two models you're talking about. Okay? It's a good question. Okay? I would say this might be the most confusing bit for refinements because, again, you got the exact opposite order of the abstract concrete and concrete abstract. But as I said, don't confuse yourself about these two. Think about there are two independent issues to solve. One is about just guard strengthening for individual events. The other one is just about whether or not a model is going to deadlock. They're different. Okay. Okay, that's good. So the next step would be, let's try to do something very routine. Given this rule, how do we formulate sequence to prove? And this one here, let's now do this together. Okay. Okay, let's see. This part here is standard. It's going to be basically the axiom, the abstract invariance, and the concrete invariance. Let me just write them down, just to be complete. Okay. The axiom is going to be the natural number, right? Basically, sorry, I didn't include it here, but I'll write it down. And also d larger than 0. Abstract invariance and concrete invariance, right? Just write them down, just to be complete. And natural number n less than or equal to d. A, natural number. B, natural number. C, natural number, a plus b plus c equals n, and also a equals 0 or c equals 0. Right? So these are the three parts. And what should this be? Sarah, what should they be? N less than d and? You mean and or? Mm-hmm, exactly, or over here. Good. Okay, so here, so these are the two abstract guard, which is going to be n less than d or n larger than 0. Of course, you're going to have the turnstile, which is over here. And for the other part, basically no way around, you're going to put them together using disjunction. Okay, let's write it down. This is like a 1, 2, 3, and 4. Okay? So you're going to have a plus b less than d and c equals 0. So the new line in the guards is as if you actually got conjunction. You want to satisfy all the guards, right? Or c larger than 0, or a larger than 0, or b larger than 0, and a equals 0. So be sure to put parentheses so you can see the actual pattern. Okay. 1, 2, 3, and 4. But of course, you will see the more organized version in the slides. But it's really important to really know how to derive them. And what's the next step? Discharge it. All right. And for this one here, if you look at the slides, okay, so that's the one we talk about. And that's the Deadlock freedom, relative Deadlock freedom, to be more precise. That's a sequence you would like to prove over here. Yeah, so here I kind of assume, since we don't really have the, well, kind of organized in a way, I don't, just for visual presentation, I didn't put parentheses. But I would suggest when you do this on the exam, put the parentheses so you wouldn't get confused. Okay. Okay. And before we prove this, okay, which I'm not going to do the entire proof in the class. The solution is already on the slides, so you guys can follow through. I'll give you a little bit guidance, like how you can decompose the proof. But you will need some new inference rule to do that. Okay, and those are the ones we just learned, which is over here. 1, 2, and 3. Okay, and if you look at the slides, oh, sorry, I kind of didn't really switch my iPad. What I just showed to you was these 3 rules that we just discussed. These are the new ones you will need for proving discharging the Deadlock freedom proof sequence. Okay, and if you go back to the slides here, you'll see that okay, these are the 3 we talk about, right? And this will be the actual proof. So basically, you start with this, and then it's quite a long proof. You will go all the way to here. So I would suggest you take this as a very nice exercise for yourself to really prove from the beginning until the end. And in the page over here, I'm going to leave it clean for you. I kind of separate that into 2 parts. Okay? For part number 1, you're going to start with this. And then consider using these rules. At some point, you will be able to show that, okay, let me copy this. You will be able to show that you can arrive in this particular intermediate sequence. And think about what we did in written test number 2. Given this, is it possible to have a sequence of inference rule application to arrive in this? I can tell you that there is. All you got to do is to figure out how to go from here to here. Once you get to this step over here, we're going to continue from here, and how to go from here into something that's axiom, inference rule. I kind of separate it into 2 parts for you. So exercise number 1, do part A and do part B. And exercise number 2, try to do from the beginning until the end on a piece of blank paper. I think that'll be the exercise advice you actually try. Okay? And of course, solution is on the slides. So guys, any questions about relative deadlock freedom? So the main thing to understand would be about the intuition. Why? We should really have the abstract guard disjunction as the hypothesis, and the concrete one as the goal to actually prove. Okay? Okay. All right, so now the next one, so we're done with the relative deadlock freedom. That's the last topic for M1. So what we should do is, we should now summarize it, and then we take a very short break, and then we can move on to the second refinement. And for the first refinement, basically, we have shown that it's provably correct. Okay? And let me just summarize over here on the page. Okay, so this is the final version we have. Oh, by the way, there's an abstract model, and that's a concrete model, right? And I want you to pay more attention to the tricky bits, which is the variance over here, right? So this is to measure the interleaving of the new events to prevent divergence. So when you study for that, you ought to make sure you understand about guard strengthening, which is about, for example, if you look at the guard over here in a concrete, it should imply the guard in the abstract. That's guard strengthening, right? And if you look at, let's say, invariant establishment, of course, you got to look at the init, the same as before. And when you look at, let's say, invariant preservation, it should be for all the events, including the old and also the new, right? To make sure they are going to preserve all the invariants that's defined in the concrete world, the concrete model. And here, convergence is about you don't really have an infinite interleaving of the new events, which will prevent any old events from happening. In that case, we have to worry about variance. And let me write a little bit more information here. And the two proof obligation we have for the variance are the net and also the var, right? So these are the two proof obligation, which you can look at the detail from the slides and also the page. And finally, we have this relative deadlock freedom. In that case, you will have to consider the concrete guard. And also you have to consider the abstract guard as well and figure out their relationship, as we actually explain very much in detail over here. Okay? So that's a summary about what you should know for the first refinements. Okay? And when we move on to the second refinement after the break, we're basically going to walk through the same process as before. But the second refinement just contains some additional variables like a state space for us to understand what's going on. But I would say, as far as the ideas are really concerned, you have learned basically almost all of them for this course. But we just need one more refinement to reinforce. All right, before I move on to a break for everybody, do you guys have any question? We're good? Okay, awesome. Why don't we take a short break and let's take attendance first. And then we can move on to the second refinements. Okay, you can get your device ready. And then I'm going to start the class right now. The poll over here. Let's say this one is fine. Okay, you can check in, please. Yeah, we're taking attendance now, so please make sure you do it in time before I close it. Just one moment, after I close it. Everybody's good? Can I close it? Thank you. All right, take a 2-minute break and then we'll come back. Yes.
Do you mind if I ask a question regarding the state space?
Yes. Visualization about state space.
Yeah, the proven DLL.
Oh, yes. Absolutely. This one here.
So,
What about it?
So regarding this one, so we said that the green circle basically is where the state doesn't deadlock in the abstract
in the abstract.
version,
But
not in the
somehow,
concrete.
not in the concrete, because you can see this state here is outside this circle.
I see. And
This-
the same thing applies for this one, right? So it
Yeah.
deadlocks in the abstract, but doesn't deadlock in the concrete.
That's right. So yeah, so for here, we're only looking at this particular state. So this state, you have two interpretation. This is a state where the abstract would not deadlock.
I see.
But it's actually a state where the concrete would actually deadlock,
Would-
which is not good. We're
I see.
introducing something that's
Which
bad.
means, and if it's like the opposite for this one, then all the bad scenarios are in here, right?
Yes, that's correct. That's
Okay.
correct. So this state here is actually fine. This is to say, this is a state where the concrete would not deadlock, but the abstract model would. In some way, we're improving something, which is
But still, it's still considered a bad scenario, right?
this one here wouldn't be considered a bad scenario for the concrete because
I see.
it wouldn't deadlock.
Okay.
Think about this state here is something that's bad for the abstract, but we have improved it to be something that's good in the
I see.
concrete.
So where do bad scenarios fall within this visualization, or they don't belong in there to begin with?
Think about the best scenario is like when you have a deadlock.
I see.
And now since we are now focusing on the refinements, you want to think about, is there any new best scenario that I introduce in the concrete?
I see.
Which is this one here. Because this is a good scenario for the abstract, but it's actually a bad scenario for the concrete.
I see.
In that case, we have introduced something that's bad.
Okay. Perfect. Thank you.
Okay, good.
I was able to join the class, but I wasn't able to answer the question. Is that fine?
You know, why don't you sign anyway? Yeah, just to be safe. Yeah. If you want to bring the pen, yeah. Before that, can you do me a favor? Can you just put a March? Today is 30th, right?
Yes.
Yeah, just put a date here. Yeah, question. 1:30 to 3:30. Yes, that's correct. Hi.
Question, could you release the solutions for programming test 1?
I wouldn't release a solution because we might have to use it for later iteration. You're more than welcome to either go over the solution during the office hour or email Andy. So either way.
Okay.
We'll go over them with you. It's
Okay.
just that we wouldn't release a hard copy of that.
Okay, sounds good. Thank you.
Rafa.
Just gonna sign in. Something wrong.
Oh, sure. Go ahead. That's fine. That's fine.
Thank you.
Okay, we'll resume in just 1 minute. Yeah. Thank you. Awesome. All right, please just get ready. We'll resume very soon. Did you answer the question or to check out the attendance?
I just didn't join.
Should be fine, I think.
Okay.
Should be all right. Yeah. Alrighty, let's resume again, please. Okay. Okay. So before the break, we talk about basically before the break, we finish off all the topics related to refinement number 1. Again, we talk about summary, so you can read over the slides as well. Okay, that's a final model. Okay. And what we now need to do is more like the final part for the case study will be to look at another refinement. So now it's really got some initial model, you got 2 subsequent refinements. Okay, so that's going to be beneficial, just to conclude about the course. Okay, we'll see how much we can go through. We'll see. Okay, so now we talk about M2. Okay, we got M0, M1 covered already. We got M2. It's an even more concrete abstraction. Okay. Like what we said before, analogy would be somehow we want to zoom in even further into the system from very high on the sky, right? Let's now take a look at the abstraction. I want you to look at diagram first, okay? We started with M0, where we are very, very high on the sky. we could not really tell the difference between an island and the breach. And we only got ML out and ML in. That's the initial model, okay? And then we move on to M1, where we lower down our altitude a little bit. So now we are able to see the one-way breach over here, where we got not just ML out, ML in, but also we got the flow of the traffic, A and C, and also number of cars in the island. So you can see now we're separate between A and B, rather than just a single compound over here, okay? And also we got the two new events, IL in and IL out, right? That's the M1. Now we're going to talk about another refinements. That one there basically is going to add two variables into the states. So we're going to talk about traffic lights. So let's say for a driver to really be able to go into the breach from the mainland, they have to follow through the traffic lights. That's definitely more realistic, right? And also similarly, if there's a car who want to leave the island and go onto the breach so they can go back to the mainland, they also have to follow some traffic lights over here. So these are the two new variables we have to look after. Okay? Of course, there should be some corresponding new events to turn the traffic light green or red. Right? There'll be two events we're going to talk about. Let's look at the convention for the naming, and then we'll look at some e-description just to draw some connection. Okay? So here you will see we got two variables. ML over here, of course, stands for mainland. And IL over here stands for island. And TL, not surprisingly, traffic lights. Okay, you just need to know the acronym. So you can see the main lane traffic light sits exactly over here to block the cars going into the breach if necessary. And also the traffic lights, ILTL, sits exactly at the edge between the island and the breach. So anybody who wants to go back to the mainland, they have to be given some permission before they can go. All right, so these are the two new variables we're introducing. Okay, and some very quick check. If I say what models are more concrete than M0, you definitely should say M1 and M2. And what models are more abstract than M1? Of course, M0. What model is more concrete than M1? Only M2. You know, etc. Right? It's relative. Everything we said about guard strengthening, let me just name just a few. To really show that this particular refinement is actually valid, we had to do things like invariance, establishment, and preservation. We have to prove about guard strengthening. And we have to prove about what else? Can you recall anything? I can recall at least two. Adrian.
Deadlock freedom or relative deadlock?
I like it. Relative deadlock freedom. Thank you. That's really important. Okay, let me emphasize it again. One more. Convergence, I like it. Thank you. That's to make sure the new events, especially the new events that are able to allow us to turn on or turn off the traffic light, they cannot just somehow keep flashing without any car that can ever go across the breach, right? That's something we'll see later. Okay, number 4 will be convergence. As you can see, all the ideas have been already discussed in the previous refinement. So now we're just revisiting the idea. But since now we got more variables to worry about, the corresponding proof sequence will be bigger. And also, if you got anything that's unprovable, you actually have to consider more in order to fix the model. That's something we'll see. But for today, we'll see. We got about 25 minutes or so. We'll see how much we can do. Okay. And let's look at one more thing. Okay, before we move on to defining the actual machine and the context. If you look at environments 1, 2, and 3, right? You remember the E description and R description. Apparently, these are the E description. And let's read it together. So this current refinements M2 over here, right, is going to address 1, 2, and 3. Okay, let's read them together. The system is equipped with 2 traffic lights with 2 colors, green and red. Right? 2 traffic lights and 2 colors. And you can see these are exactly the 2 traffic lights we have introduced. Okay? And the traffic lights control the entrance to the bridge at both ends. That means you got 1 over here, you got 1 over here on the edge, over here and here. And the cars are not supposed to pass on the red traffic lights, but only on the green one. So that's the important assumption we have to make. Otherwise, if the driver doesn't really follow through the traffic light, in that case, our model may have to be much more complicated. Even maybe to say if somebody tried to go across the red light, maybe there should be a camera over here, or there should be some alarming system over here. So that would be much more complicated. So we don't really talk about it for now. Okay? So what you have to know, just make a note. Environment number 3 is important without this assumption, and 2 would have to be much more complicated. For example, we may have to get some red light camera. Okay, that one just a very important concept to clarify. Okay, and if you when you study for this, of course, you can also go to some very early slides when we first talk about this case study, kind of summarize about which refinement and which model is trying to address which E&R description. So you can also go over them when you study the whole thing. All right, let's see what we have. Okay, MLTL, ILTL. Oh, and then one more thing to say. That's if you think about what's happening over here. Right, let me just look at my notes very quickly. So there is one new word that we have to learn. Okay, if you talk about the variables, so the variables we have over here is simply just n in the initial model. In the M1, we know that we got A, B, and C. And remember in the events that we define over here, ILN, ILOut, MLL, MLN, we no longer define their action or guards in terms of N. So N was completely replaced by A, B, and C. It's not like an inheritance, right? Because in inheritance in Java, you have to inherit all the attributes from your parents plus yours. It's not like inheritance. It's just a replacement. That's something to note. In this case, abstract variables replaced by the concrete variables. But now, in the case of M2, we have something that's slightly different, just to see the possibility. In M2, as you can also see in the diagram, we still keep A, B, and C. That means when you try to define the guards and also the action, you can still use A, B, and C. In addition to it, we also got 2 new variables, MLTL and ILTL. So it's more like an inheritance in Java. You inherit the attributes from your quote parents, A, B, and C, A, B, and C. In addition, you have some new attributes in the child classes, right? So here, let's write it down. From here to here, number 1, abstract variables are inherited. And number 2, new concrete variables. And you will see that in this particular phenomenon, it's called superposition. Well, you will see the word actually in the slides, right? Okay, so if I really mention about superposition in the exam, you should really know what they really mean. They simply mean when you try to create a concrete model over here, you're not trying to replace all the abstract variables and replace them with a new one. Not really. You want to reuse them in addition to some new variables you want to introduce in a concrete model. Okay? Okay, so after that, let's now take a look. Okay. Oh, so we don't have time to actually talk about the third refinement, which will be the very final refinement in the original textbook, in which case we can also introduce the idea about sensors and actuators. We wouldn't have time. For those of you who are really engaged into the course, maybe in the summer, if you want to dive into it, feel free to check out the textbook, which I already made available to you. You can check out the third refinement. But I wouldn't test you on that on the exam, so don't worry. Okay, and then, environments constraint 1, 2, 3, which we also went over. And we are obliged to prove all the proof obligation that have to be applicable to the refinement. We'll see some of them today, hopefully, and we'll see some of them on Tuesday. Okay, let's talk about the state space and also the constraint on the state space, which will be invariants. Let's talk about them first. So we have, let's now go over them quickly. Okay, so this is just to remind you, we are now addressing 1, 2, and 3, e-description. And let's look at the static part, the context. So we define some set called color. And we have two constants here, red and green. Think about them, they are more like a enumerated type in Java. So each one of them, to implement it, they will have some unique integer identifiers. But for now, just remember, if we mention about red and green, they're simply different constant. Okay? Yes?
So imagine for a second that instead of being red and green light, we had a case where you could have red, yellow, or green lights. Would it be possible to, would it be possible to start with red and green lights and then refine it and further things to red, yellow, or green? Or
Yeah, absolutely. It's definitely one possibility.
I thought about that initially, and then I went.
Okay. Yeah, so Nathan has a very good, very interesting possibility, which is completely legitimate. So here, we are having basically only two possibilities, red and green. But that's not what you will actually see in the normal traffic light, right? There will be another color, the ambient color. In that case, you can definitely try to refine that into another color, if that's going to make any change to the event definition. Yes. Okay, anyway, so for now, let's omit that possibility. So we got color, and we got red and green. The axiom will be pretty straightforward. The color will just be a set containing just two members, green and red. Green here, and red over here. Okay? And obviously, green is not equal to red. Okay? That'll be the axiom we have to deal with, static part. Any question about the static part? Yes? I see what you mean. I think in the set, you mean the numeration over here, right? Yes. So, not too sure if I mentioned that in the math review lecture. Maybe I didn't. Okay, let's say this. It is okay for you to write something like this, to say 2 and then 2. Wouldn't be the normal way you write it, right? You should say 2 and 2. But this will be, of course, equivalent to just 2. So now, since we try to enumerate about these two constants over here, we want to make sure they're still going to result in a set with cardinality 2. So that's why we want to make sure they're distinct. Hopefully that answers your question. Okay, good. Nice concern, absolutely. Okay, so let's now talk about the variables, and then we can work out some invariants very quickly together. Yes? No, we don't need to. Because here, in some way, we just say, first of all, red and green, they're constant. And then the types are basically specified over here. We're saying that green should be a member of color, and red should be a member of color. Right? So it will be as if, for this part over here, we're basically saying green, I'll just say G, is a member of color. And also the red is also a member of color. But I think this one here just kind of more concise to write it. Okay. All right, let's now talk about the variables. Okay? As I talk about superposition, so we just say we got A, B, and C, and then we got MLTL, we got ILTL. So here is on paper, so we just mention all the variables. If you ever want to do this on Rodin, which we wouldn't cover, for this course, you don't really have to explicitly define this ABC anymore. You will simply say M2 refines M1, and then we got these two new variables. But on the paper, it's good to mention all of them. Okay, just a distinction. All right, so we got A, B, and C, we got MLTL, and we got invariants. We have 4 invariants to start with. Okay, so these two are the more like a typing invariants. We say MLTL should be a color, ILTL should be a color, right? That means it can be red or green, red or green. That makes sense. So this one here will be the typing invariants. And as we said before, if you only have, let's say, only typing invariants for your model would be under-specified. So you definitely want to make sure you have some additional invariants that's actually going to address some safety concern or something else. Okay. And for invariant 3 and 4, let's now, well, they're pretty simple, but I think it's good to work out them quickly together. For invariant, again, you can see the naming convention. You can see invariant 2. 2 over here talks about M2. And we're enumerating them from 1, 2, 3, 4. And later on, when you actually want to prove, let's say, invariant preservation, we'll talk about abstract invariants and concrete invariants. So these 4 will be the concrete invariant in this case. What will be the abstract invariants? Where should we get them from? M0 or M1? M1. Yes, that's what we should do. Okay, just remember. All right, so let's work out these two invariants pretty quickly. Invariant number 3, okay? Let's say being allowed to exit from the mainland means there should be limited cars and also no crash. Okay, so let's put them here. So that means if somehow a car is actually allowed to really get to here, that should really mean the state should be in such a way that you will allow it to do it. What should be the overall structure for this particular invariance? Sounds a bit conditional, right? Conditional in the sense that we only worry about the case where we are allowed to exit from the mainland. What if this is now when cars are not allowed to really exit from the mainland? In that case, we don't care. It's more like a conditional. And whatever you want to do conditional in logic, what should you use? Implication, right? So here, the means over here really suggest that you want to use implication. Okay? And then, how do we formulate the antecedents? What does it really mean when a car is actually allowed to exit from the mainland? What would the car actually follow, Nathan?
So it would mean both. So this could mean either that MLTL is green, or that or eventually that the event for the car exiting the mainland is enabled. But I think the answer mostly is ILTL is green.
Yes, I agree. Because now we say that in this refinement here, we assume that the driver is going to follow through, the traffic light. Yes. So this is to say, if this happened to be green, then what should be the consequence, right? So we want to say for invariant 2, 3 over here, let me use a different color. For this one here, we're going to say ML TL equals green. Should imply something here. All right? That should imply somehow the cars are actually within the limits, and also there should be no crash. Yeah?
So we need to have A plus B plus C less than B. And we have to have C equals 0. And we have to have ILTL is red.
ILTL is red, I agree. Ultimately, that's something we'll get into a little bit later. But for now, let's put something a little bit simpler. Yeah, we might need it at some point later in other part of the model. Okay? So it turns out we just have to write something like this. Okay, I'll put it out and then we can discuss if you got any question. Number one, we should say A plus B and then less than D, right? It should be bounded. And also, the opposite side over here should be 0. Yeah. I absolutely agree with you. Somehow, I can tell you the reason that the author actually put this one to begin with was because he thought this would be some nice way to illustrate. Maybe you forgot something that you should have included in the invariance. So we're going to see that having here, not talking about the traffic light should be red. For the other one, you're going to have some unprovable sequence. So we're going to add something to address this later. So let's follow through the logic for the author. Yeah, but that's absolutely a very good concern. We'll do that later. Yeah, for now, let's pretend we actually as dumb as the author thought we are, just for now. Okay. Okay. So this will be the one. You can see here should be A plus B less than D. That should be limited cars. And here, no crash, right? Can anybody tell me or try to explain why not? Well, you think that should be more appropriate. So I'm adding a possibility where A plus B equals D. That's pretty accurate, actually. So think about what's happening here. When you have the antecedent here, MLTL equals green. If this is green, that means as soon as this turns green, there could be one car that just want to go right to the bridge. In that way, you're going to have A plus 1. If you already have equals over here, you're going to exceed the capacity right away. Okay, I'm going to write down the rationale here. That's something you want to think about. Like this one should not be there. Okay, because number one, MLTL equals green means a car can move to the bridge. In that way, A will become A plus 1. Number two, if we already have A plus B equals D, in that way, A prime plus B prime is going to be larger than D, right? Because it's already equal, you're trying to add one more. So it's going to go above the limits, right? It's a very minor thing, but important to justify why we wouldn't put the equal as a possibility. Right, so boundary case is actually quite important for your model. So I think in many scenarios, the reason that you got unprovable sequence is you got the boundary cases wrong. Okay. All right, think about this. Right. All right, the second one. Let's say we talk about the other one. Let's say being allowed to exit from the island. That means we are able to do here, right? That means some car should be in the island. Well, otherwise this should be, that some car should be in the island and also no crash. How do we formulate this? This one may be easier, I think, right? This one here, being allowed to exit from the island. That means we got some traffic light here that's actually green. Oh, sorry, that's not green, apparently. This one here, right? So you will have some car wanting to go here. In that case, antecedent should be ILTL equals green. That implies some car should be in the island and no crash. Okay? Well, that one, some car should be in the island. That should be B larger than 0. And no crash. That means the opposite should be equal to 0. Yep. All right, any question about this? I think today the main goal is to get familiar with the new concrete state space, and then we can do a little bit of, maybe we can do a little bit more discussion. We'll see how much time we have. We have about possibly 5 minutes, no more, no less, 5 minutes. We can still a little bit more. And then for next Tuesday, the last class, we'll try to move on to some discussion about some proof obligation. Whatever I cannot finish wouldn't be too much. I will assign some video watching for you before the exam. Okay, that'll be the plan. Okay, let's now talk about just one more, okay? Let's talk about ML out and IL out. Okay? One thing I'm going to write down for your reference, but you want to double check yourself if that's really the case from the previous discussion. ML out, number one, is an O events, which already exist in M1. Let's see. Does any one of you remember the guard for ML out from before? Of course, you wouldn't memorize it. That's okay. I wouldn't expect you to memorize it. But let me write it down. The abstract guard is, let me say a little bit more from M1. Would be C equals 0, right? The opposite traffic should be 0. And A plus B strictly less than D. That was the abstract guard. So now the question is, does it make sense to copy and this one here and paste it here? That's the question. Mm-hmm. And the judgment is not really based on logic, because if we just copy and paste, it will be logically equivalent. But we're more talking about, does it really make sense for this particular event to have such guard? Yes or no? I agree, but let me write it down first. That will be the answer, but we want to have a little bit more confirmation. It turns out, for this concrete guard, you don't need this, okay? You're going to say ML TL equals green. So we talk about this particular event, ML out. Why is this guard more appropriate than this one here? Adrian.
Well, because of the invariant to _3, if this new guard is true, then so is the old guard. But this also incorporates the new features of the traffic lights.
Yes, we definitely have to somehow, have some antecedent, like a mode exponent. That's something we'll do a little bit later, absolutely. But something even higher level. Go ahead. Yeah, that's pretty much on the right track. Think about what ML out is. ML out over here is more about for the driver to follow. For driver to follow. Now, if I'm not a driver, I want to go to the bridge. Do I have to know A, B, and C? Do I need to know how many cars are actually on the bridge? Do I need to know how many cars are in the island? Do I need to know what the maximum capacity is? Should I be bothered by that? Not really, right? All I need to follow will be, should this be green or red? That's it. So that's why for ML out over here, we only have to make sure MLTL is green. The next question is, where should this guard go? Rafa. We need to actually, because here we talk about, we're assuming that the light is going to work. So the driver will just follow, either green or red. But now, where should we still should put this guard here. It cannot just disappear. It should still appear somewhere.
Isn't it just invariant rate?
Nope. Invariant are like a constraint for your model. But we need actually some, like an actuator to actually sense, so we need some systematic, we need some check to make sure this condition is actually the case. Not the invariant. Okay, so let me tell you. Sorry, I know I'm up to time, but I'll just say one more. What's going to happen is, there will be a new event we have to introduce called MLTL. So this will be an event that's actually going to turn the light to be green. So before we decide to turn the light to be green, we should really check this condition here. And once the light is turned green, ML out may occur for the driver to follow. So that's kind of the sequence we're introducing. I'll write it down and then I'll let you guys go. So this will be guard for a new event, and we'll start from here. MLTL. All right, and if you guys got any more question about the programming test, drop by my office hour or speak to Andy. Otherwise, I'll see you guys next Tuesday. Take care.